Alright, welcome. In this video, I'm going to be working both parts of the practice final exam for Algebra 2. So let's just start with number 1. And I'll tell you that, this test is a multiple choice test, but this practice test, I took the choices off and, switched up the problems a little bit. So, you're not going to be asked to sketch 4 graphs. It's probably going to be like, here's a graph, which of these 4 equations matches the graph? Or, here's an equation, which of these 4 graphs matches the equation? And so I'm going to go in here and just make 4 sketches. Right, for 1/2 x squared, we know what y equals x squared looks like. 1/2 x squared would just be like a little wider. It's a regular parabola, but maybe it's wider than usual. And I'll just label that A. For B, y equals 1/2 x, that's going to be a line with slope 1/2 and y-intercept 0. So just right about like that. Okay, for C, 1/2 x cubed, okay, we know what x cubed looks like. 1/2 x cubed would be, vertically compressed by a factor of half, or we could just say look pretty much like y equals x to the 3. Maybe just a little bit flatter. And then y equals 2 over x. That's like 1 over x, but vertically stretched by a factor of 2. 1 over x would kind of look like this, and if we're not going to label the y-axis, it doesn't really matter what our scale is. Well, that would be 4 function types that we definitely need to know what the graph looks like. Alright, number 2, talking about horizontal asymptotes, and this is one that came up a lot in class when we were working this. With a horizontal asymptote, I think the main thing that you need to remember for Algebra 2 is that y equals 1 over x, that function, its graph has a horizontal asymptote at y equals 0, because the bigger x gets, the smaller 1 over x gets. If you're taking 1 and you're dividing it by bigger and bigger numbers, you're going to get a number that's closer and closer to 0. So for f of x equals 3 over x, I'm going to say the horizontal asymptote is going to be y equals 0 also. Because same story, 3 over x, 3 is fixed, x gets bigger and bigger, 3 over x gets closer to 0. Okay, for b, the 4 over x is going to go towards 0 as x approaches infinity. So as a result, f is going to get closer and closer to 1 plus 0. This would be like horizontal asymptote y equals 1 plus 0. And so y equals 1. Or you could think of it as a graph of y equals 4 over x shifted up by 1, because that addition of 1 on the outside. Okay, and so if we shift everything up by 1, that horizontal asymptote, it's also going to get moved up by 1. Now part C, depends on how you approach this in your Algebra 2 class. In my class, we didn't deal with this a whole lot, especially where we couldn't factor and have a common factor on top and bottom. But you go to try to factor x squared minus 3x minus 17, and it's not going to get you anywhere, right? Because you can't think of factors of negative 17 that add a negative 3. So I guess the other thing that we could do to try to investigate this function would be actually do long division. And that's something we haven't done a whole lot lately. X squared, negative 3x, and negative 17 divided by x minus 4. I'm going to think to myself, what do I multiply x by to get x squared? And that's going to be an x. I distribute the x over the x and the negative 4, so it'll be x squared minus 4x. We're going to subtract this. And we're going to get, okay, x squared minus x squared is nothing. Negative 3x plus 4x is going to be 1x, and then we drop down the 17. And then I ask myself, what do I multiply x by to get x? And that would be just a 1. And I distribute the x and the minus 4. I subtract that, and I'm going to get negative 13. And that's going to be my remainder, so minus 13 over x minus 4. So if we're looking at y equals x plus 1 minus 13 over x minus 4, and we think about what happens as x gets bigger and bigger, well, that 13 over x minus 4, that's going to get closer to 0, but x plus 1, it's not going to have any discernible behavior, right? X gets bigger, x plus 1 is going to get really big, minus 0. Okay, that's going to go to infinity. If x goes into the negative direction, the 13 over x minus 4, that's still going to go towards 0, but I'm going to have negative infinity plus 1, and that's still going to be really negative, right? And so this one's going to have no horizontal asymptote. Now, in your class, you may have been told, okay, if the degree on top is bigger than the degree on bottom, then just in general, there's not going to be a horizontal asymptote. We just didn't talk about that a whole lot in my class. I figured we'd save that for pre-cal, because that's going to be an asymptote. No, pardon me. No horizontal asymptote for that one. What I will say about this thing, though, is that I could kind of sketch the graph of this for you. We know that y equals x plus 1 looks, like a line with slope 1 and intercept 1. And let me think about this for a second. As x approaches 4 from below, we're going to have subtracting a negative number, and whoops. And then when I'm doing that, let's see, okay, yeah, it's going to be really big and positive, so it's going to have a vertical asymptote like that. But otherwise, it's going to kind of just pick back up on its overall pattern of being y equals x plus 1. And so it's going to have like what we would call a slanted asymptote. But we didn't talk about that much in Algebra 2, at least in my class. So we're just going to say bigger on top, no horizontal asymptote. All right, next. If square root of 5x plus 3 equals 7, what's the value of x? Okay, so let's just solve this equation. So when we've got a radical and we're trying to find x out of the inside of the radical, what we're going to do is isolate the radical and then take both sides to an appropriate power. And so that's going to mean subtracting 3 from both sides, so I'll have square root of 5x equals 7 minus 3 is 4, and then, okay, to get rid of the square root, I'm going to square both sides, and just remember when you square both sides of an equation, we have to check our solution to make sure it's valid, and we didn't run into like an extraneous solution, but I don't think that this one's going to make that happen. So square both sides, and I get 5x equals 4 squared is 16. I'm going to divide both sides by 5, and get x is equal to 16 divided by 5. Right, next, if 5 to the negative third is written as a simplified fraction a over b, what are the values of a and b? Okay, so this is a problem that definitely works better for multiple choice, but, I wanted to make it a little bit different. So I had to kind of come up with this a and b thing. In multiple choice, it's like, which of these numbers is equal to 5 to the negative 3? But for us, okay, we're going to say, remember that x to the negative a power is equal to 1 over x to the a power. That's the big thing that we need to know here. So if we have 5 to the negative third, that's going to equal 1 over 5 to the third power. And then 5 to the third power is 125. Okay, and that's a simplified fraction, so the answer would be a equals 1 and b equals 125. All right, here we've got ourselves like a log equation. And so with a log or an exponential, kind of like the radical, the first job is to isolate the log, isolate the exponential. This one's already got that going for us. So, okay, we've already got log base 2 of 3x minus 1 equals 5. So I need to get rid of the log, so I'm going to use an exponential. And the exponential should have the same base as the log. So I'm going to say 2 to the power of both sides should be equal. 2 to the log base 2 of 3x minus 1. That should equal 2 to the 5. And then we know that, the 2 and the log base 2, they kind of undo each other. And so I'm just going to kind of get rid of those like that. And then we'll say 3x minus 1 is equal to 2 to the 5, which is 32. And I'll add 1 to both sides and say 3x equals 33, divide by 3, and we'll get x equals 11. All right, we're going to sketch some more graphs. I think first I should probably write down like the equation that represents each of these situations, and then we can write sketch a graph of each equation, because that's what we're most used to. We're most used to going from an equation to a graph, not from a word to a graph. So direct variation, that's where y, is just some multiple of x. So y equals k times x. Okay? If we called it y equals mx, we might realize it's just going to be a line with some slope that has y-intercept 0. So we already drew one of those earlier on number 1, but inverse variation is y equals some number divided by x. Also drew one of those on number 1. Exponential growth, y equals a to the x, where a is a number that's bigger than 1. And y equals 1 over a, if a is bigger than 1, to the x power. That would be exponential decay. That could be a to the negative x. You could also call that a to the x, where a is a number between 0 and 1, whatever you want. Okay, with direct variation, okay, y equals k times x, that's just going to be a line that happens to go through the origin. For y equals k divided by x, okay, like 1 over x looks like this. If k was a negative number, we'd have kind of a different looking graph. It'd be kind of upside down looking from that. Assuming k is positive, that would be that general look of the graph. For exponential growth, if a is the base and a is bigger than 1, it's curve up like this and have a horizontal asymptote y equals 0. And for exponential decay, it's pretty much the same, just the opposite horizontally. It gets closer to 0 the bigger x gets. And so that would be a sketch of the graph of each of these 4 scenarios. Alright, this next one asks us to find the value of x that makes the equation true. And we've got 2 to the 3x equals 8 to the 2x plus 1. And we could, maybe try to solve this by taking a log of both sides. But if you recognize that 8 is a power of 2, then we can solve this, a little bit more directly. We can say to ourselves, alright, 2 to the 3x is equal to 8, which I know is 2 to the 3rd power to the 2x plus 1. And one of the big themes in Algebra 2 has been we got power of a power. That's where we're going to multiply the exponents. So 2 to the 3x is going to equal 2 to the power of 3 times 2x plus 1. So I need to distribute the 3 over the 2x and the plus 1. And I'll say that's 2 to the 6x plus 3. And if these two things are equal, then you can kind of just look at it and see that the exponents are going to have to be equal. So I'm going to say that 3x is going to equal 6x plus 3. Maybe I'll subtract the 3x from both sides. Subtract 3, divide by 3, and see that x is going to equal negative 1. Alright, for simplify the rational expression, that's where we're going to look to factor this thing and cancel off anything we can. So I'm thinking to myself, I'm going to try to factor the numerator. So what two numbers multiply to 12 while adding to negative 7? That would be negative 4 and negative 3. So I've got x minus 4 times x minus 3. I'm going to divide by two numbers that multiply to negative 21 and add to 4. So I'm thinking 7 and 3, because that's really the only things I know that multiply to 21. And so that would be positive 7, negative 3, so x plus 7, x minus 3. And then I can kind of cancel off identical factors, and I'll be left with x minus 4 over x plus 7. And, this expression would be equivalent just as long as x was not equal to 3. Because if x was equal to 3, then, the simplified expression, it would, have a value. Whereas for the original one, you have 0 over 0, which is undefined. All right, number 9. Now this one is a multiple choice question because there was just no way I could make this question into a free response. Which of these numbers is closest to the value of log base 2 of 33? Well, if you really internalized what I said about, a log, that it's just an exponent, and it's the special exponent I would put on 2 to get 33 in this case, so it would be like 2 to the what power equals 33. Okay, we know 2 to the 5 equals 32. We've already run into that, I think, yeah, in this problem set. So it should just be a little bit bigger than 5, right? So I'm going to say 5.1. But if you didn't just completely internalize that, mindset that I'm talking about here, where 2 to the what equals 33, what we could do is we could just write ourselves like an equation. Say that log base 2 of 33 is equal to x. If you didn't have that, I need you to know that logs and exponentials, they undo each other. So I would take 2 to both sides power. So 2 to the log base 2 of 33 is equal to 2 to the x, and these things undo each other, so 33 equals 2 to the x, and then you're back in the same place. Okay, what exponent do I put on 2 to get 33? And that's going to be something a little bit bigger than 5, which would be 5.1. Okay, here's one that definitely also works better as multiple choice than just open response, but, I was really committed to making these ones that you had to, write out your own answer. So this one, it's going to be just hey, which of these 4 multiple choices is equivalent to log base a of 3x to the 9y to the 2z? Now this just says expand in terms of the plain log. So we're going to need to use the log properties. And so let me kind of copy down the 2 that we really need here. We're going to need the product and the power properties of logs, right? If we have the log of a product, we can split that into the sum of 2 logs. And then also if we've got an exponent on something inside of a logarithm, we can swing that exponent kind of around the front of the logarithm. I'm not going to go in and explain why these things are true. I did that, in an earlier video, and you could just go back and search for that, log properties, and I give a lot of detail on why these things are true. I'm going to actually copy in the other 2 log properties that you need to know for this class, but we're not going to use for this problem. We've got the division to subtraction property and the change of base formula. We're gonna need these for this problem, but you do need to know these for Algebra 2 and for pre-calc. In this case, with log base a of 3x to the 9 y to the 2z, I'm going to be using that first property, right here. I'm going to be using that to split this into log base a of 3 plus log base a of x to the 9 plus log base a of y to the 2 plus log base a of z. So I'm going to say this expression is log base a of 3 plus log base a of x to the 9 plus log base a of y to the 2 plus log base a of z. And we want this just in terms of log base a of x and log base a of y, and not x to the 9 and y to the 2. So then we're going to use that second property to swing those numbers around the front. Let's say that's log base a of 3 plus 9 times the log base a of x plus 2 times the log base a of y, and then just plus 1 times the log base a of z. And that's how we would expand this thing in terms of those logs. All right, next we've got the domain question. And maybe for this one, I might add in another question, like what's the range of f? It might be good practice for us too, so... ask what's the range also. And I think what I need to remind you is kind of like the domain and range rules for square root, logs, and rational functions. All right, so for a square root, like we're taking the square root of u. That's going to be defined only when u is not a negative number. So like u is greater than or equal to 0. If we're taking log of u, or u might be some expression like involving x, we can only take the log of a positive number. So that's going to be where u has to be greater than 0. And for a rational function like 1 over u, that just can't equal 0. So those are kind of the three scenarios we need to be aware of. So for the square root one, I'll look at this one and say, all right, x plus 4 is on the inside of the square root, so that needs to be greater than or equal to 0. So if that's true, then x is greater than or equal to negative 4. For a natural log, that's the same as any other type of log. The argument, the thing on the inside, that needs to be greater than 0. So we'll say that's x is greater than negative 4. And for a rational function, 1 over x plus 4, the denominator can't equal 0. So I'm going to say x plus 4, that can't equal 0. Solve that non-equality and get x equals not equal to negative 4. And then maybe I'll go in and write the rules about range too. All right, for a square root function, when we write that square root, we mean the positive square root. So as a result, we're going to say that y is positive. But we can take the square root of 0 and we would get 0. So y can be greater than or equal to 0. With the log is an exponent that we would put on b to get u, whatever u is. But there's not really any restrictions on what type of exponents we're allowed to use. Okay? And that's how I always explain, like y is any real number. And these log functions, they always have range all real numbers, at least in this class. And for rational y equals 1 over u, y just can't equal 0. Because if we take 1 and we divide it by any number, we can get all sorts of stuff, we just can't get 0. Because the only way we could get 0 out of a fraction is if the numerator is 0 and the denominator is non-zero. And since these functions are, like relatively simple, they're not really anything beyond just the square root of something, the log of something, and 1 over something. And really the excitement's on the inside of these functions. Those are just going to be the ranges of these functions. For a, the range is going to be y greater than or equal to 0. For the log, it's going to be y in any real number. And for the rational function, y can be anything besides 0. If we'd seen f of x equals the square root of x plus 4, minus 5, then y would have been greater than or equal to negative 5 because that's shifting down by 5 that a subtraction on the outside represents. Okay, but I think that's enough for this problem. All right, finding the inverse of the function, we're just going to solve for x. So we're going to replace y with, or f of x with y, so y equals x to the third plus 5. I think I'm taking a lot of room with these. Okay, and I'm going to just solve for x. It's the way we know how. So I'm going to subtract 5. And x equals the cube root of y minus 5. And that's a formula for the inverse of the function. But what if it said which of these is f inverse of x? We'd need to go ahead and switch x and y and call y f inverse of x. So f inverse of x is going to be the cubed root of x minus 5. All right, and for b, okay, y equals 3 to the x plus 5. Okay, we're going to solve this for x. So we're solving an exponential equation. We have to isolate the exponential. So I'm going to subtract 5 from both sides. Okay, and then to get the variable down out of the exponent, I'm going to have to use a log. So I'll take the log with base 3 of both sides. If I'm taking log base 3 of 3 to the x, that'll just give me x. And if I've solved for x, I've got the inverse of the function, so I just replace y with x and say, no, not f, pardon me, that's going to be g inverse of x equals log base 3 of x minus 5. For part C, we've got something multiplied on a log function, so I'll say y equals 5 times log base 3 of x. And so I need to isolate the log, get rid of that 5. Now you could use that power property, but I don't think that's the way to go here. I'm going to divide both sides by 5, and I'd get y divided by 5, or 1/5 of y, and that'll equal log base 3 of x. If I want to get rid of the log, I need to use an exponential. I need to take 3 to both sides power. So I'm going to have 3 to the 1/5 of y equaling 3 to the log base 3 of x. That's going to be x, because the exponential and the log, they undo each other. And so I've got x solved for, I've got the inverse. I'm going to say h inverse of x equals 3 to the 1/5 of x. Okay, next I've got x equals 16 to the a over b. Okay, rational exponents. If a is 4 and b is 7, then I'd have 16 to the 4 over 7. Okay, write it in radical form. So that means, with a root. So if I see 4/7, it's the 7th root of 16 taken to the 4th power. Maybe we could have also said that this is 16 to the 4th. That number is 7th root, okay? These are the same thing. We need to be able to recognize, especially in like a multiple choice setting, that these are the same. Okay, and if a is 3 and b equals 4, write x in simplified form. So that's going to be like actually evaluating. Hey, we don't know how to take the 7th root of 16, or probably 16 to the 4. That's going to be a really big number. Okay, so we're not really able to do anything. We can just write it in radical form. But for 16 to the 3/4, it looks like we'll be able to work with this. So 16 to the 3/4 equals the 4th root of 16. I always recommend you deal with the denominator first to keep the numbers manageable, right? Because we don't want to take 16 to the 3rd power. You might be able to, but no, well, just not. So that's going to be, okay, the 4th root of 16 is 2. So this is going to be 2 to the 3rd, and that will be 8. And that'll be simplified form. Okay, now here's some good algebra 2. We're going to multiply some polynomials. So, with anything bigger than FOIL, I recommend just using the box. So I'm going to say x squared plus 3x and plus 5 multiplied by x and plus 2. Make sure I, distribute all of my terms. Make a little box over here. Fill it in. X times x squared, that's x cubed. Okay, 3x times x would be positive 3x squared, positive 5x, positive 2x squared. 2 times 3x would be 6x, and 2 times 5 is 10. Then I'm just going to add all this stuff together. So I'm going to have x to the 3 plus 3x to the 2, and I see there's another x to the 2, so it's going to be 2x to the 2 here, 5x and 6x plus 10, and then I'm going to combine some like terms, right? I can take the 3x and the 2x, and I can combine them to make 5x squared. 5x and 6x, that's going to combine to make 11x, so I'll have x to the 3 plus, 5x squared, and then plus 11x, and plus 10. All right, now this next one, we've got f of x being a rational function, and they're going to just ask us kind of some trivia questions about it. What are the x and y-intercepts on the graph of f? Okay, for the y-intercept, that's where x is equal to 0. Okay, so we're going to plug in 0 for x, and we'll get f of 0 equals 6 times 0 plus 7 over 0 squared minus 5 times 0 plus 4. That's going to be 7/4. Okay, so that's going to be the y-intercept. Is x equals 0, y equals 7/4. For the x-intercept, that's going to be where y equals 0. Okay, y is f of x. Okay, and this fraction can only equal 0. You can write out the whole fraction equals 0 and then multiply by the denominator, or you can recognize that it's only going to be able to equal 0 when the top is equal to 0. So 6x plus 7 equals 0. Okay, I can see that the denominator is going to be factorable. So, and I can also see that the 0 of the numerator is going to be a fraction. So I know that this 0 of the numerator, it's going to be a real x-intercept. It's not going to be like a hole in the graph or anything. So 6x equals -7. Divided by 6, and x will be -7/6. Okay, and that would be the x-intercept. X equals -7/6, y equals 0. And next, we'll find the equation of any vertical asymptotes to the graph of f, or explain why it has none. Okay, so if we're going to do that, the vertical asymptote, that's where the denominator equals 0. Specifically, where the numerator is also not equal to 0. So we're getting like a number that's not 0 divided by 0. So I'm going to say to myself, all right, where is x squared minus 5x plus 4 equal to 0? And this is a quadratic. Okay, we've got it set to 0. It's the only way we can solve one of those. Provided it's not just like x squared minus some number. And I'm going to think about, I can factor this. Okay, two numbers that multiply to 4 and add to -5 would be -4 and -1. So x minus 4 and x minus 1. Neither of these are factors of the numerator, like I was saying earlier, because the numerator was only 0 when x was -7/6. So I'm going to say, all right, this is true when x equals 4 or when x equals 1, and these are the equations of my vertical asymptotes. X equals 4 and x equals 1. Okay, I think we could also ask about the horizontal asymptote here, and I know it doesn't say it on the paper, but I'm going to answer it. And for a horizontal asymptote on this one, because the degree on the denominator is bigger than the degree of the numerator, okay, as x gets really large in the positive or negative direction, the denominator is going to just be much larger than the numerator. Okay, it's going to grow much faster because of that second power, and as the denominator grows faster than the numerator, you get a bigger denominator, you're dividing by more, you end up with less, and it gets closer to 0. So I'm just going to say that because the degree of the bottom exceeds the degree of the top, the horizontal asymptote is going to be y equals 0. All right, now number 16's got another equation for us to solve, and this has got, x in a fraction, so I think there's a couple of ways you could go here. I think what I'm going to do is I'm going to just get a common denominator, because that's been the most frequent thing we've done. So I'm going to say this divided by x is going to be my common denominator. So 6 over x minus x, so I'm going to need to multiply on top and bottom by x. So I get, x squared over x. That makes sense. I could, reduce that to minus x. And 5, well, I guess I'd have to call that 5x over x. That also, that looks a lot like 5. So now that I've got a denominator on all the terms in the equation, I can just get rid of that denominator and say, all right, that means 6 minus x squared equals 5x. Set this thing equal to 0 because it's got more than one power of x involved. So 0 equals x squared plus 5x minus 6. And this one is one of these tricky ones to solve because it's like, is it 3 and 2 or is it 6 and 1? Two numbers that multiply to -6 while adding to positive 5, that would be positive 6 and -1. So x plus 6, x minus 1, this is going to be x equals -6 or x equals 1. With these, when we're doing these rational equations, it's good that we check to make sure that we don't have an extraneous solution. And an extraneous solution would be something that causes us to divide by 0, which feels like 0 in this case, but that's not one of the answers we got. So both of these are going to be valid. I will also point out, though, that a person could have proceeded here by adding the x to both sides and saying 6 over x equals x plus 5, and then multiplying both sides of the equation by x to end up with something very similar to what we had before, right? Then that would be a perfectly valid way to go on this equation. All right, good. I'm glad we got one of these on here too, because I saw that other radical equation. I didn't remember that this one was on here. Okay, so we're going to find the values of x to make the equation true, and it's going to be another one where we're going to have to square both sides. But this one, we're going to have to square the right side, and the right side's a binomial, so we're going to have to just be careful. So if I square the square root of 3x, that's going to give me 3x. And hopefully we all agree on that. But I just got to be careful when I'm taking x minus 6 squared, because that's not just going to be x squared minus 6 squared or something like that. It's going to be, I'm going to have to use FOIL. So I'm going to say 3x equals x minus 6 times x minus 6. And when I actually distribute that, I'd get x squared. I'd get negative 6x and another negative 6x. So it'd be a total of negative 12x, and 6 times 6, or negative 6 times negative 6, that's going to be positive 36. I'm going to subtract the 3x from both sides. X squared minus 15x plus 36. And I'm going to try to factor this, right? If I can't, I'll use the quadratic formula, which is something we need to know. Let's see. All right. Numbers that multiply to 36. There's a lot of these, right? Like 9 and 4, but those don't add up to 15. I think it's going to be two negative numbers because they're going to multiply to a positive number and add to a negative number. And so 9 and 6, 12 and 3, yeah, there we go, 12 and 3. I also think 18 and 2 is kind of close, but it's going to be 12 and 3, so x minus 12 times x minus 3. Right? And then I'm going to get x equals 12 and x equals 3. But remember, at one point in this solving this equation, I squared both sides. So I'm going to have to check my solution. And I'm going to see that when I do that, x equals 3 is going to be an extraneous solution, because what happens is I get the square root of 9 equals 3 minus 6. And we've got that square root. We mean the positive square root. So this is not true. This is equal to positive 3, but that's negative 3. Okay, these are not equal, so that's an extraneous solution. So it's only x equals 12 going to work here. And you can think about it, square root of 3 times 12 does equal 12 minus 6. Number 18 is also one of these rational equations, so we're going to go for a common denominator. I'd say we're going to need the 9 and the x plus 9. So x plus 9, I'm going to multiply this on top and bottom by 9. And then I've got minus 1 over 9. I'm going to need to multiply that by the x plus 9. But I don't want to change the value of the fraction, so I got to multiply by the x plus 9 on top and bottom. So I'm essentially multiplying by 1. And this will equal negative 9 over x plus 9. And then we're going to be multiplying in that 9 here to get a common denominator of both x plus 9 and 9 on all of the terms. So I'm going to get rid of it now that I've got a common denominator on all the terms, and then multiply. So 9x minus an x plus 9 is equal to negative 9 times 9 is negative 81. So I've got 9x minus x minus 9 equals negative 81. 8x minus 9 equaling negative 81. I'll add 9 to both sides. So that would be, I think, yeah, negative 72. Divide by 8 and get x equals negative 9. Okay, and then when I do that, I need to check my solution to make sure I don't have an extraneous solution. And sure enough, if I go back and look, you know, at the original equation with x equals negative 9 plugged in, like starting right there, but also right here, I've got division by 0. And although like undefined and undefined are the same thing, we're not going to be saying they're equal to each other. Okay, so this is going to be an extraneous solution. Oh, whoops. Didn't know I had access to a black highlighter in this situation, so we're going to scratch through that and say it's extraneous. And if the only thing we got was an extraneous solution, then okay, this equation has no solution. Okay, number 19 is asking for the end behavior of the graph of the function. And that's just going to be like what happens as x approaches infinity and what happens as x approaches negative infinity. Okay, with f of x, this first f of x in part A, this is degree 3 positive x cubed, so it's a positive leading coefficient. So if it's an odd degree with a positive leading coefficient, it looks essentially like y equals x cubed, which is to say as x approaches infinity, positive infinity, y approaches positive infinity, and as x approaches negative infinity, y is going to do the same thing. Y goes to negative infinity. Okay, for part B, this is degree 5, also an odd degree, but this has a negative leading coefficient because of the negative x to the 5th, so it's going to look like y equals negative x cubed. So pretty much the exact opposite. As x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y is going towards positive infinity. And for C, we've got an even degree, degree 4, positive leading coefficient, coefficient 5, so positive leading coefficient. It's going to look, in some ways like y equals x squared. Both of the arms are going to go up. So we'll say as x approaches positive or negative infinity, y is going to go to positive infinity. Okay, I bet since I've got 4, this one's going to be the opposite. Yep, degree even, leading coefficient negative, so it's going to look like y equals negative x squared. So as x approaches positive or negative infinity, y is going to approach negative infinity. And that would be kind of like all 4 of the end behavior type situations we might run into in Algebra 2 for a polynomial. All right, for the exponential function f, what is its percent rate of change? Okay, I need to remind you that for an exponential function, it's like f of x equals some starting amount. Usually we call that a or p or something like that. Times, some number to the x power. But at the very beginning we said, okay, we could use a percent rate of change by saying 1 plus r, where r is the percent rate of change. Okay, so really we're looking at this, and we've got all these numbers just taken to the x power, so we're saying, okay, what am I actually doing here? Okay, for f, I'm multiplying by 1.02, which is going to be 1 plus 0.02. That represents 2% growth. For b, 0.91 is less than 1, so this is going to be an exponential decay situation. Okay, I could look at this as 1 plus negative 0.09 to get 0.91. So my rate of change would be negative 0.09, or a negative 9% increase, or you could just write that as a 9% decrease. But if the percent rate of change is negative, that means things, getting smaller, the amount is decreasing. For part C, 2 to the x, okay, so if I've got 2 to the x, that's going to be 1 plus 1. But r is the percent rate of change, and 1 is 100%, so I'm going to say this is a 100% increase because r was a positive number. And that's how I find the percent rate of change. Now we're about to see another one of these as we flip over into the calculator section. Is that a blank page? Yeah, here we go. All right, so we're going to be moving forward into part 2. This one allows the use of a calculator, and so I'm going to use that anywhere that I can, because that's what I want you to do. That's why we studied the calculator stuff at the end of the year, was so that you could know when to use it and how to use it, and I'm going to give it to you on half the final. Okay, now the first one is, given this function, what's the approximate percent rate of change? E to the negative 0.6x. Okay, so this is a little tougher. Even though you're allowed to use a calculator, we're going to say, all right, so f of x in this case is equaling 23 times 1 plus the percent rate of change to the x power. If I look at this, and that's not the color highlighter I want, this 1 plus r to the x situation is going to be, I can figure that out from e to the negative 0.6x. So I'm going to set up a little equation over here. I'm going to say, all right, so I want a pen. So 1 plus r to the x equals e to the negative 0.6 to the times x. But then you need to recognize that thing from studied repeatedly in Algebra 2, that multiplication of powers is when we take a power of a power. So we could look at that as e to the negative 0.6 to the x power. We're going to need a calculator for this. Ask it to tell us what's the value of e to the negative 0.6. And I can say, okay, that's 0.5488. So I'm going to say 0.5488 to the x equals 1 plus r to the x. And I think that pretty clearly means that 1 plus r equals that 0.5488 number. So if I was trying to solve for r, I would subtract 1 from both sides, and I can even do that with a calculator and just be like answer minus 1, and get negative 0.4512. And if they asked what's the approximate, percent rate of change in this situation, if I had negative 0.4512, that would be 45.12, because to go from a decimal to a percent, we move right by 2 places. And since it's negative, I would say that would be a decrease. And that's a problem that we need to know how to do for this test. Okay, for this next one, finding all the values of x to make the equation true with a third-degree polynomial, we could sit and try to, maybe factor this thing by grouping, but we wouldn't get very far. We'd look at what we could factor out of the first two and the second two, and there wouldn't be any way we could, go beyond that. Okay, we could try the rational root theorem, but there's going to be a bunch of possible rational roots because 18 and 4 have a lot of factors. I don't like that. Also, you've got a calculator available to you, so we should be utilizing that. So let's bring in the calculator, and we're going to go into the y equals menu, and maybe I could make this a little bit bigger. Let's see, can I do that? Yes, we'll just enlarge this by quite a bit. So in y equals, I'm going to type in the function, and then I'm going to graph this thing. I'm going to zoom to the standard window because I just, I always want to have hope that it's just going to work out and I don't have to adjust the window. There's 1, 0, I'm kind of expecting 3. Okay, but it could be that there were 2 imaginary solutions, and that might be what I'm looking at here. Okay, so I'm going to start by calculating the first 0 that I can see, and that's between -1 and 0. I'll give it a guess, and I get -3/4. So x equals -3/4. And now, if I'm looking, I might zoom out. Okay, so zoom out on, sure, suggested that point as a place to zoom out. Doesn't seem like a bad idea to me. I am not seeing any turning around here, and we don't really have any calculus abilities. Maybe I'll zoom out one more time. And okay, I'm not seeing any other zeros, so I think the other two are complex. And if that's the case, well, then I'm going to, unless I'm just totally missing something here. Let me make sure I typed in the function right. No, I did not type the function in right. I didn't get that 28. Okay, so that's what happens when I don't have kids in front of me pointing out my errors. Okay, maybe this will work a little bit better. So I'm going to definitely need to get rid of that y equals -3/4. There we go. That was a second one and a third one. I've got 3 zeros on screen. This is looking good for me. All right, so I'm going to calculate a 0 between, there's another one between -1 and 0, but it kind of looks more like -1/2 to me. Yeah, x equals -0.5 or -1/2. We can calculate another 0 between 0 and 2. Looks like it's going to be 1.5. Yep, so x equals 1.5, or 3 divided by 2. And then the last one, that is looking like a whole number, 2, 3, 4, 5, 6. And that seems believable because 6 is a factor of 18. I'm just going to make sure I know it's between 5 and 10. And yeah, I get x equals 6. Okay, so those are the values of x that make the equation true. Okay, for simplify the rational expression, this is one that we are not going to be using a calculator for, right? Because we're using calculators that don't have computer algebra in them. I'm just using a graphing calculator. So what we need to do is factor the numerator. Okay, so I'm thinking of factors of, oh wait, and I need to change, I'm changing this one to plus x to be, as useful to you as possible. I decided I was going to do that a couple days ago when working with people in class on this. So factors of -12 that would add to +1 would be +4 and -3. And then in the denominator, okay, I'm looking for a greatest common factor, and it looks like it's just going to be x, and I'd have x times 2x plus 1. Now if I'm dividing, I'm going to be flipping and multiplying the second thing. So I'm going to have 2x squared plus 9x plus 4 on top, and x squared minus 9 on bottom. I know how to factor x squared minus 9. That's the difference of two squares. That'll be x plus 3x minus 3. Okay, and I see some stuff about ready to cancel. But to do 2x squared plus 9x plus 4, that's one we haven't done in a while. So I'm going to just kind of remind you of what we do here. Okay, so we're going to take the 2 and the 4 and we're going to multiply them. That'll make 8. So I'm looking for two numbers, I'll usually call them m and n, that multiply to equal 8. I don't really care if I've got a software update ready to install. And that add to 9. Okay, so it's going to be 8 and 1. And so I take that 9x and I turn it into 8x plus x. So 2x squared plus 8x plus another x plus 4. And then I do group and factor. What can I factor out of the first two? That'd be 2x times x plus 4. And then there's nothing in common to the second two, so I just factor out a 1. See, these factors do match the x plus 4s, so I factor them out, and I've got x plus 4 multiplied by 2x plus 1. And so that's how I'm going to factor it and put it over here. Now, if you can just like look at this or like, kind of suspect what the factors are going to be based on the context clues from the other factors, then good for you. But if you need to work it out every time, like I do, then there's nothing wrong with that. Alright, and now I'm going to go in and cancel off things that are identical. Okay, I've got these x minus 3s, they're the same. I've got these 2x plus 1s, they're the same as well, so I'm going to get rid of them. And so now I'm left with 2 powers of x plus 4 in the numerator, and x plus 3 in the denominator. Now, if I had to, I could expand those, but I think that that's how the answer choices look on the equivalent problem on the test, is that it's factored up for us. Okay, here we've got an inverse variation, so that's one of the formulas we need to know. If we see x and y vary inversely, then y is some number divided by x. Okay, you could also say that the product of x and y is always constant in an inverse variation situation, but in my Algebra 2 classes, we just said y equals some number k divided by x. And so we're going to use the, condition that we were given, x equals 27 when y equals 5, so 5 equals k divided by 27. And let's see, 27 times 5, well, that'd be 100, plus 7 times 5 would be 135. How I feel about that? 15 times 8 is 120. So yeah, 135, 15 times 9, yeah. Okay, k equals 135. So my actual equation for this inverse variation is y equals 135 divided by x. And if x equals 15, y will equal 135 divided by 15. And I just figured out that that was equal to 9, but if you were unsure, what you could do is, because this is the calculator section, you could bring out that calculator and say 135 divided by 15. And, notice that that's going to be 9 that way. Alright, so number 5, find all values of x that make the equation true. Okay, now, I'll show you how a person would do this by hand after I show you how I want you to do it. Okay, I want you to be like, okay, this is an equation, but I've got a calculator available to me, so I'm going to use that calculator. I'm going to type in y1, this left side of the equation, type in the right side in y2, graph this thing on the standard window, and look for an intersection. Okay, and it's like, where is my blue graph? Okay, and that I must need to adjust my window. Okay, log of a function doesn't really make sense when we're taking the log of a negative number, because it'd be like 10 to what power is a negative, and that never works. So I'm going to need to change up my window. Probably I'll let x be from 0. No, really, you can look and see that x is going to need to be bigger than 25 in order for this to work. Right, because of, if x is less than 25, then that second expression, this log right here, that's not going to be well defined. So I'm going to go in, I'm going to do maybe x from 0 to 100, because I'm really not sure what's kind of going on here, and I know log functions grow very slowly. And so, okay, there's my log function. There, okay, I see an intersection, right over here, so I'm going to calculate the intersection between blue and red, give it a guess, and get x equals 29. And that's going to be, like a really good way to solve equations when you're allowed to use a calculator. Now, I'm going to show you how to solve this without a calculator, but I'll also show you that this is like a little bit treacherous and that there's ways that you can be like led astray. Okay, we're going to use a log property, right? That if we have two logs added together, I can multiply their arguments. So I've got log with base 10 of x minus 4 times x minus 25. And I'm going to actually just multiply those right now. I'm going to do FOIL. So x squared minus 4x minus 25x plus 100, because negative 4 times negative 25 would be positive 100. And that's going to equal 2. Now I'm going to take 10 to both sides power. I'm going to say, all right, 10 to the log base 10. Well, that's just going to leave me the argument. Oops. 29x plus 100 equals 10 to the 2 equals 100. And I subtract 100 from both sides and I get x squared minus 29x equals 0. So I'm going to try to factor this, and I've got a common factor. And this would lead you to think that x was either equal to 0 or equal to 29. But if we go and we look closer at x equals 0, if we plug it in here and there, we've got two logs that are both undefined added together equaling 2. There's no way that, like, undefined plus undefined could equal 2. So we're going to say x equals 0 is an extraneous solution. And so that's why I really like the idea of using the calculator to solve this one, because you don't get that x equals 0 solution if you use the calculator, because it's not a real solution. Alright, here's another one. Like, we could definitely do this one without a calculator if we had to, if it was like the most important thing. But it's not. We're allowed to use a calculator here. So what we're going to do is use the change of base formula. And I'm going to use the change of base formula because I'm not assuming that everyone has the nice color addition calculator, because actually if you ask me to borrow a calculator, I'm not going to give you one of those. I'm going to give you a TI-83 because those are just the ones I have to loan out. So what we need to do is remember that, log base b argument a is equal to natural log of a divided by natural log of b. You could use common logging, really use any base log you like, but I know that all of these calculators, they all have a natural log button on them. So what we're going to say in our case is log base 4 of 512, that's going to equal natural log of 512 divided by natural log of 4. And so for us, we're going to say, all right, natural log of 512 divided by natural log of 4. Have the calculator do that for us, and we're going to get 4.5. I will point out, though, if you've got one of these nice calculators like I'm working with here in this virtual display, you can go over here to Math and scroll up from the bottom and do log base. And then that would do log base 4 of 512, and that kind of just really trivializes the question. But, kind of have a couple of easy questions on the test for you to just use the calculator on. Make sure you know how to punch your buttons. So that would be another way we could get 4.5 if our calculator has that command. Right, the next this is another one that I tried to translate from multiple choice that I don't know how well it went, but okay, if we've got, a linear function on the tables, we have to have a constant first difference. So, when I'm saying here that I went from 5 to 2 by subtracting 3, I know that every time I'm going to have to be subtracting 3. So 2 minus 3 is negative 1, negative 1 minus 3 more is going to be negative 4, and then negative 7. That's how it would fill out for a linear table, because it's always the same difference. For quadratic, we're going to have a little more freedom here because that's the constant second difference. So here, when I went from 6 to 2, I decreased by 4. And so whatever I do over here, I just have to have not the same decrease or increase or whatever. I can really make this anything I want. Maybe I'll make this minus 2. Or maybe actually I'm going to make it minus 1. Okay, but if you wanted to make it minus 3, negative 4, negative 3, negative 2, negative 1, that's an option you have, whatever you want. So to go from 2 minus 1, that would just be 1. And then think about the second difference here. Okay, and that's going to be an increase of 3. That needs to be constant, so I need this to be a plus 3 as well, meaning that now I need to increase by 2. Okay, so that would be 3, and, oh, whoops, let's see. Oh yeah, I was confused by my colored arrows. Okay, but then, this time, this next one, I'm going to need to be, again, adding 3, so this will be a plus 5, and to go from f of 5 to f of 6, that'll be going from 3 to 3 plus 5, and that's going to be 8. But there's going to be lots of right answers for this one with quadratic. But in multiple choice, it's like which of these represents a quadratic table. We're just looking for the one that has a constant second difference, and there would only be one right answer. Okay, for f of x is exponential, we're going to see a constant ratio. Okay, so when I went from 2 to 6, I multiplied by 3. So I need to see that consistently when I'm multiplying by 3 every time. 6 times 3, that's 18. 18 times 3 is 54. 54 times 3, all right, we could use a calculator if we needed to be sure. Okay, but 50 times 3 is 150, and 4 times 3 is 12, so I'm going to add those together, and now we get 162. And if f of x represents an inverse variation, this is not one that we did in my class, at least with a table, but it's one that we definitely could do, because y equals some number k divided by x, or as I mentioned just a few minutes ago, x times y equals k. So if they give us 2 and 60, I know that x times y equals 2 times 60 is 120. So I say 3 times what is 120? That's 40. 4 times 30 is 120. 120 is definitely divisible by 5. You know, in some ways, dividing by 5 is like multiplying by 2. So it's going to be, 24. And 120 divided by 6 would be 20. Because all of these pairs, I need to have a constant product. Right. Mandy bought a computer for $3,900. It's expected to depreciate, that means get less valuable, 12.5% per year. Okay, so this is an exponential decay scenario when we've got this percent rate of change. So the amount, function of time, is going to be equal to the starting value, 3,900, times 1 plus the rate, which was negative 12.5%, to the number of years. If we want to know the value of the computer in 4 years, that would be f of 4. That would be 3,900 times 1 minus 0.125 to the 4th power. Okay, now there's no sense in us actually computing 1 minus 0.125. You might realize that's 0.875, but that's just risky arithmetic we don't need to engage in because we've got a calculator. So I'm going to type this expression in just like I'm seeing it, and let the calculator do the work. And see that that is going to be $2,286.11. $2,286.11 would be the approximate value of the computer after 4 years. Composition of functions. That's something the computer's not going to, the calculator's not going to help us with all that much. So unless we have a computer algebra system, they can just do it for us, but we're not going to do that. So f of g of x, wherever we're seeing x in the formula for f, we're replacing it with g of x. So that's 1/3 of g of x minus 2. And g of x is 12x plus 6, so that's 1/3 of 12x plus 6, subtract 2. Distribute the 1/3 over the 12x and the plus 6. And then I'm going to get 4x. That was interesting. And then g of f of x is wherever I see x in the formula for g, I'm replacing that with f of x. So this is going to be 12f of x plus 6. And that's going to be equal to 12 times f of x, which was 1/3 x, minus 2 plus 6. So when I distribute that, I get 12 divided by 3 is 4 x's, minus 12 times 2 plus 6. And so I'd have 4x, negative 24, add 6 back, that would be negative 18. And that's going to be f of g of x and g of f of x. All right, here's another simplify the rational expression. So we're going to get more factoring in. We're thinking about numbers that multiply to negative 10 and add to positive 3. That's feeling like negative 5 and positive 2. We're multiplying these fractions, so we're just going to multiply straight across. Two numbers that multiply to 4 and add to 4, that would be positive 2 and positive 2. And then I'm going to divide by, two numbers that multiply to negative 15 and add to 2, be 5 and 3, positive 5, negative 3. So x plus 5, x minus 3. This isn't looking good so far. Then, negative 6 -1, that's going to be x minus 3, and x plus 2. Makes me wonder if I was maybe supposed to be dividing here when I was copying the problem. Okay, this is not the best. Okay, so not a whole lot's going to cancel here. I'm just going to have one of these x plus 2's canceling. And, okay, this would simplify down to x minus 5 multiplied by 2 powers of x plus 2 over x plus 5. Maybe I copied a negative wrong. You know, like if that had just become a negative, then no. I feel like there's something off with this problem. But then 2 powers of x minus 3, but I'm just going to work this one as I'm seeing it. Okay, so I did have a range problem on here. So f of x equals the square root of x plus 5 minus 6. Okay, so what's going to happen to the parent square root x function on this one is going to shift left by 5 and down by 6. Okay, and we know that square root of x, always comes back with a number that's greater than or equal to 0. So this thing, this square root of x plus 5, that's going to be greater than or equal to 0. But then I'm going to subtract 6. So the output is going to be y is greater than or equal to -6. Because it could equal -6 if x was equal to -5. I'd be taking the square root of 0. That's 0, and 0 minus 6 is -6. So that can happen, but otherwise, the square root of x plus 5 will be a positive number. For a cube root function, okay, I didn't talk about that before, but we can do the cube root of anything. So I'm going to say all real numbers here. Y is an element of the set of real numbers. And same for the log function. I talked about that earlier. I was talking about range. Log functions, cube root functions, those have full range. Okay, now, cube root function has a full domain, but log function, the domain of this h of x, that would be where x is greater than 3. Okay, this one, I don't know. We could solve this with the calculator for sure. And I think that'll probably be what I do first. So I'm going to go in and in the y equals menu, clear out the last equation I solved and say e to the 5x and 40. But I'm going to have to adjust the window, right? Because I'm looking for y equals 40 as my intersection. I'm probably going to need to, I might go back to the standard window, then, have it stop graphing and then edit the window from here. Because I'm hoping, I think it should be between -10 and 10, because e to the 50 is a number that's much bigger than 40. But I'm going to do maybe from 0 up to 50. I always like to change the scale on those so it's just not too crowded with dots. Okay, so we see like really fast exponential growth. We see an intersection. We will calculate the intersection between blue and red, and that'll happen at 0.7377. And I really do recommend you solving this equation that way, but if you feel like you just got to solve this one by hand, we can definitely do that. So what I'm going to do to get this 5x down out of the exponent is I'm going to take a log of both sides. And since the base is e, I need to base my log to be e, so I'm going to take the natural log of both sides. And the natural log of e to something, or the natural log of the special exponent I put on e to get this thing, so the exponent I'm going to put on e to get e to the 5x, that's just 5x. And that's going to be equal to natural log of 40. And so x is going to equal natural log of 40, all divided by 5. And, I could have the calculator do that. I could call for the fraction bar and say on top I've got natural log of 40. But it's important that we close off that natural log, especially if we're not using a fraction bar, because we're not doing the natural log of 8. Right? We're doing the natural log of 40, and then we're dividing by 5. And that's where I get that 0.7377 or 7378. Okay, you can round it however you want. Multiple choice, there's only going to be one of those two answers. Right, so here we've got Mr. Williams opening a savings account with a starting amount of money. So we need that formula, that compound interest formula. A equals P times 1 plus R over N to the NT power. Okay, where principal, the starting amount, is going to be $9,100. 1 plus interest rate is 5%, that's 0.05. We're going to divide by the number of times per year interest is paid. So that would be quarterly, that's n equals 4. And that's going to be our function a of t. That's part A. And part B is the amount of money in the account 10 years after the account was opened. So a of 10 is going to equal 9,100 times 1 plus 0.05 divided by 4 to the 4 times 10 is 40. And that's what we're going to have the calculator do for us, because we don't know how to take that number to the 40th power. So 1 plus 0.05 divided by 4 to the 40th power. And I get $14,956.94. So $14,956.94. All right, we've got, okay, we're going to transform this thing. We're going to shift a parabola up by 5 units and left by 2 units. All right, so up by 5 units is like taking f and adding 5 on the outside. And left by 2 units is going to be, actually, hold on. I meant to do, okay, up by 5 units in red is plus 5. And left by 2 units is where we replace x with x plus 2. Okay, so if y equals x squared, or f of x equals x squared, I'm going to be squaring x plus 2. And then I'm going to be adding 5 on the outside. Okay, but if we're having to like recognize the correct parabola, you know, the equation might look like this. I don't know what the test looks like. I haven't looked at it in a couple days. Or it might be, you know, like simplified, and we need to be able to do that. So I'm going to just do that. So we need to be able to recognize either of these as the equivalent version. Combine some like terms. Get x squared plus 4x plus 9. Okay, now we've got an absolute value equation. And, okay, because this is an equation, I'm going to want to solve it using the calculator, but I will show you how to solve this one by hand, because it's something we did in this class, but it was a really long time ago. So I'm going to grab the absolute value out of math number. Okay, and that's true for all of the TIs, the 83s and the 84s. 3x plus 5. And then I'm going to graph the other absolute value, so math number absolute value, 2x plus 20. And, you know, if you remember, we can get 2 solutions to these things. And so, okay, I'm still graphing on the old window, but let's see. I couldn't see the whole V for red, so I probably need to adjust my window to include some more negative values. I'll just do negative 20 to 10. See what happens there. Because I kind of liked the way the graph looked here. Okay, I do think that, you know, because of the way that you can't even see what I'm doing. I didn't have it on screen, pardon me. I don't know how long it's been gone. But because I'm over here, and you can see that these 2 lines are getting closer to each other, I can see there's going to be another intersection later. So I'm going to again adjust the window to include negative 20 to, I don't know, maybe positive 40. Really make sure I've got these intersections in. I'm going to change the x scale to 10 though. Okay, so these V's are looking very different each time, but there were 2 intersections. Okay, so I need a little bit more in y. Okay, so this was really one where I had to adjust the window a lot, but that's good, because that's one of those things I've noticed in AP Calculus and in, you know, like the pre-AP classes too, the College Board stuff, they really like to see you adjusting that window to find solutions to equations. Something we definitely need to be able to do. Okay, there we've got ourselves 2 intersections. So let's calculate the intersection between blue and red. We're already kind of close to one. That's x equals 15. And if we're solving by graphing, we don't have to worry about extraneous solutions. I'm going to find an intersection between blue and red. This time I'm going to give it a guess of negative 10 though, and because I know it was like negative, and I don't want to get that same solution x equals 15 a second time, so that's where I'm going to get x equals negative 5. Okay, now if I got rid of this, I probably could have done this a little bit faster by hand, if I'm being honest. You know, this is prone to errors, right? Hand computation errors. So if two absolute values are equal, then it could be the case that the things on the inside of the absolute value were exactly the same. Or it could be the case that they were exactly opposite. So like 3x plus 5 was the negative of 2x plus 20. Then they would still have the same absolute value. And so I could distribute this and say 3x plus 5 equals negative 2x minus 20. Whoops. Hold on. Minus 20. And then I could add the 2x to both sides. Subtract 5. And see that x was going to equal negative 5. Both of these things, I would, since I'm solving an absolute value equation, I should probably plug them back in to check and make sure I'm not going to get any extraneous solutions, but absolute value equals absolute value, that's not something we're going to be running into. All right, so that's all for this problem. Okay, find all solutions to the inequality. This one we're definitely going to want to do with the calculator. So I'm going to graph both of these things. Yes, I remembered I kept this the same for you so you wouldn't have to do as much typing. And I'm going to zoom back to the standard window though. Okay, yes. And so we want to know where is the absolute value greater than 8. So the absolute value is the v, and where v is above 8 is where the blue curve is above the red curve. And so I'm going to just calculate the intersections. Blue curve, red curve, guess, get x equals 1. Maybe I'll actually, kind of draw this. And then the other intersection, I'm assuming it's going to be an integer, but blue curve, red curve, looks like it's around negative 5. That's, negative 4 1/3. Okay, so negative 4 is negative 12 thirds, and extra third would be negative 13 over 3. That's goes showing you can't just assume it's going to be a whole number. And the absolute value is greater than the constant 8 over here. So when x is greater than 1, or when x is more negative than negative 13 thirds. Okay, now these next two, you could use the calculator for these if you wanted to, but I think that you could just solve these, more logically without the calculator. So with this one, I'm going to add 5 to both sides and get 3 times the absolute value of x plus 2 is less than or equal to negative 2. Always the first step with these is kind of isolate the absolute value, so absolute value of x plus 2 is less than or equal to negative 2/3. But the absolute value of x plus 2 is always going to be a positive number, or maybe 0. At the very least. So it's never going to be less than negative 2/3 because it's never going to be equal to negative 2/3. And it can't be negative at all. So this one has no solution. And then for part B, this one, I'm going to solve for the absolute value by subtracting 2 from both sides, so the absolute value of x minus 1 is greater than negative 5. The absolute value of x minus 1 is always either positive or 0, so that's always greater than negative 5, so that's always true, and I just might say all real numbers. All right, number 18, write an equation for the graph shown below. So I see it's a v, so I know it's kind of like I'm starting with the y equals absolute value of x. But I might say absolute value of x minus h plus k with some number on the outside. H and k are going to be the coordinates of the vertex. So I'm seeing that the vertex is where x equals 3, y equals 2. So I know that I'm going to have h equals 3 and k equals 2 in this situation. And a is kind of the slopes of these lines, right? At least in absolute value, if it's pointing up, we're going to see a positive slope. So I go from this point, I go over 1 and up 2. So I know that the slope is 2. I'm going to say 2 times the absolute value of x minus 3 plus 2, that's going to be y, and that's going to be my equation. Had this V shape been going downwards, then it might have been like negative 2 or something like that. Okay, number 19. If f of x equals the absolute value of x and g is 3 times f of x plus 2, describe the transformations of f that would produce the graph of g. So I'm going to go in and look at each of these things that's been done to f of x and say, like, okay, what's that What's the impact of that? So if I replace x with x plus 2, that's going to be a shift by the left, or to the left by 2 units. And then on the outside, I'm multiplying by 3. So a transform on the outside is going to be a vertical change. A multiplication corresponds with a stretch or a compression. And so if I'm multiplying by 3 on the outside, it's going to be a vertical stretch by a factor of 3. And there you go. You could maybe try to use a calculator for this, but again, I think it's going to make it slower. Nothing faster than just knowing the rules and knowing how to use them. All right, now the last one, number 20. Let P of t represent the number of lions in an endangered habitat, and t is the number of years after development started on the new construction. All right, we've got this model for the population. When is the population going to fall below half of what it was at t equals 0? All right, so I guess what we first need to know is, population at t equals 0 is going to be P of 0 equals 500 times e to the 0 power. E to the 0 power is going to be 1, so this is just 500. If you need to verify this with a calculator, you go on ahead. What we're interested in is half. So I'm trying to solve the equation P of t equals 250. So what I'm going to do is I'm going to use a calculator for this, right? There's no sense in, you could, I don't say there's no sense. There's definitely, it's good to be able to do it by hand, but let's make this a little bigger and get these functions in that we need. So 500 e to the negative 0.13 t and 250. I'm going to show you another way to solve this with the calculator. I think that is actually a little bit better. I'm going to zoom to the standard window, but that's not going to do very good for me because I know I'm looking for y equals 250. So this is just not really doing it. It's still graphing. What a mistake. Okay, right. So the window over here, I'm going to scroll down and make the y max 300. Maybe we'll do a y scale of just 100. But I do feel like it probably should be, within negative 10 to 10. Okay, I'm seeing the curve. Yeah, there we go. We're going to see an intersection there. We're going to calculate the intersection between blue and red. Give it a guess. And that's going to be 5.332. Oh, but it said 10th of a year. So that's just going to be t equals 5.3. Okay. Now, I was thinking, I never noticed this before, where it says, hey, I'm looking for where blue and red are running into each other. That's nice. I feel like I had something else to say about this. Yes, totally. All right, better way to solve this. Okay, so that we wouldn't have to adjust the window. If P of t is going to equal 250, then we should be able to subtract P of t minus 250 and get 0. So I could kind of clear this out. And then I can zoom to the standard window, and it's much more likely to be, something I can see the solution of, because I'm just looking for it to run into the x-axis. And there it is, right? So I could just, at this point, calculate a 0, left bound 0, right bound 10. There's only one 0 in there. And have it search and get that same 5.3 answer that way. And I actually like that a little bit more as far as its durability for long-term solving equations using the calculator, because you won't have to spend a whole bunch of time moving around the window. And that's the last problem for this practice test. This practice test was very comprehensive. Like I said in class, if you know how to do all the problems on this practice test, you will know how to do all the problems on the exam. And conversely, if there are any problems you don't know how to do on this practice test, there will be a problem you don't know how to do on the real exam. So if that's the case, if there's any of these that you don't understand after watching me work it on video, I would encourage you to come talk to me before you take that final exam, okay? Because I'd be happy to work with you on any of these problems. Okay, so that's all for this video. Thanks for watching.